In this video, we're going to trace through the quicksort. Now, there are a couple of efficiencies and improvements that have been made to the quicksort algorithm, but really the partition method is the workhorse of quicksort. So understanding how the partition method works is the most important thing. And we'll talk about some of those little improvements like sort first, middle, last, and using insertion sort, but really don't focus on those. Really focus on understanding how the partition method works, because again, that's kind of the heart of the quicksort method. So quicksort starts by being invoked with an array, and this quicksort implementation is recursive. So we call a helper method. The helper method is actually going to be the recursive method that calls itself, sending in the first and last positions in the array. So starting at position 0 and going up to position length -1. Now, typically, if our size of our array is less than some minimum, we won't use quicksort. We'll use a slower sort like insertion sort. Remember that the slow sorts are perfectly fine when we're dealing with really small sets of data. So a common minimum size might be 10 or something like that. So if you're giving me an array of size 10, or once I recursively get down to sorting subsections of the array that are size 10 or less, I'm not going to use quicksort anymore. I'm going to switch over to one of those inefficient sorts because it's okay on a small data set. I'm not going to show that in the trace today, but that's typically how quicksort is implemented. And then what quicksort does is it calls a partition method. And again, the partition method is the key here. What partition does is it separates the array into kind of 3 sections. A section of the array that's smaller than some value, the value, and a section of the array that's larger than some value. And that value is called the pivot. So we have all values that are smaller than the pivot on the left of the array. Then we have the pivot value. And then we have all the values that are larger than the pivot on the right of the array. So that's what partition does. Now, these smaller and larger sections of the array are not sorted. We just know that everything here is less than the pivot and everything here is greater than the pivot. But the order within those smaller and larger sections is jumbled. It's not sorted. Just everything here is less and everything here is more. So let's not think about for a moment how partition works, but let's just, say we had that method that did that. What we can then do is we can say, okay, we know now that pivot is in its proper place in the array, right? Because everything here is smaller than pivot and everything here is bigger than pivot. So pivot is in its final place. Okay, I've put one element in its place. So what I can do then is I can just recursively call this same method on this section of the array and also on this section of the array. So basically say, okay, let's do that again. Let's now call this method with the first index still being first, and the last index being where the pivot is -1, so basically up to but not including the pivot. And then also recursively call quicksort on everything after the pivot, so starting with the new first index of pivot +1, pivot index +1, and going up to the last position. And then recursively we'll do the whole thing again. So we'll find the pivot of this smaller part of the array, meaning somewhere in the middle of this array there'll be a pivot, and everything smaller will be less than that pivot, and everything to the right will be greater than that pivot. And we'll do the same thing on this half, and so on and so on. We'll just recursively divide down until we get to a section of the array that's smaller than our minimum size, and then we just sort that little section. Okay, so that's how the high-level quicksort method works. This seems pretty simple, right? This idea is pretty easy. Hey, if we could find something somewhere in the middle of the array that put it in its place, and then just recursively sort the other 2 halves and do the same thing with them. That's pretty straightforward to understand. The partition method itself, though, is where things get a little complex. So this is where, again, all the work happens in quicksort. So that's what we're going to trace through, is how the partition works. And essentially how partition works is it finds a pivot in the section of the array that you're looking at, and we then kind of trace from the left, looking to find values that are as long as we are searching or looking at values that are smaller than the pivot. So we're basically looking for something bigger than the pivot. When we find it, we stop. And then we search from the right, looking for something smaller than the pivot. And when we find it, we stop. And then we swap those 2 things. So we take something that's on the left but is bigger than the pivot, and we swap it with something that's on the right that's smaller than the pivot. So now those elements should be in their proper place. And then we keep searching. And we do that until kind of we cross over. Okay, so let's take a look at what this actually looks like with a trace. So this is our array. It's got 13 elements, indices 0 through 12. So first is going to start out being 0. Last is going to start out being 12. And we're going to call the partition method on this. So we're looking to return pivot index. So whatever this partition method returns is going to be the pivot index sent back to the quicksort method. Okay, so inside of partition, the first thing we do is we find mid, which is first plus last divided by 2, so that's 6. And then the next line of code is the first of these efficiencies. One of the efficiencies that we do to make quicksort more efficient is we sort these 3 elements. Sorting 3 elements isn't hard, right? We can do that with any sorting algorithm because it's a very small set. So we basically want to sort 2, 4, and 8. So 8 is the biggest, 2 is the smallest, and 4 is the middle. So we sort the values at first, mid, and last. Don't worry too much about why we do this. This helps improve the efficiency of quicksort, and it's kind of the first step. If you don't do this, quicksort still will work fine. Partition will work fine. Your indices would be a little bit different, and your method will be a little less efficient. So we're just going to do that without talking too much about the details. And again, don't worry too much about the details of why we do that. Okay, so that's that step. The next step is we swap the values at position mid and last minus 1. So this is mid, index 6, and this is last, index 12. So last minus 1 is index 11. So we're basically swapping the 4 and the 3. And then we're saying that pivot index is last minus 1. So pivot index is this one. And the pivot is going to be the array at that position. So the pivot for our partition method is going to be 4. All right, so that's our pivot. Okay. So now we can start doing the partition. So we begin putting the index from the left at first plus 1. So here, it's going to be our index counting in from the left. And index from the right is last minus 2. So last minus 2. And for now, we're not going to be using first, mid, and last anymore. So I'm just going to kind of get them out of the way so we can just focus on the partitioning. Okay, so now we're going to go until we're not done. We start out with assuming done is false. So we're going to loop while done is not true. So while done is false. And we're going to have, we have a little while loop here. While the value at index from left compared to the pivot is less than 0, which means, well, this value is smaller than the pivot. So is 9 smaller than the pivot? Pivot is 4, so no. So we immediately stop this while loop. Okay, we didn't even get to go through it, and we pause here. We then look at this while loop, and we say, okay, well, the value at index from the right, which is 7, is greater than the pivot, which is 4. That's true. So what we want to do is we want to decrement index from the right. So we take index from the right, and we move it down. And then we do that while check again. So is the element at index from the right greater than the pivot? Well, now it's not. 2 is not greater than 4, so we stop. So we've gotten through these first 2 while loops. And here we have an assertion that whatever value is at index from the left is greater than or equal to the pivot. 9 is greater than or equal to 4. That's true. And whatever value is in the array at index from the right is less than or equal to the pivot. And 2 is less than or equal to 4, so that's true. So our assertion is correct. So now, if our index from the left is less than our index from the right, which it is, now we go ahead and we swap the values at index from the left and index from the right. So we swap the 9 and the 2. We basically take an element smaller than the pivot and move it over to the left. And we take an element greater than the pivot and we move it over to the right. And then we move forward the left index and move left to the right index. So we move these closer to each other. And now we get back up to this while loop because we never changed the value of done. Note that this is in the else statement, so we did not execute that. So we're going to go through this while loop again. So we say, okay, well, the index on the left is pointing to something smaller than the pivot. Is it? Is 7 smaller than the pivot? No. So we, again, don't get into this while loop. We just pause there. And then we say, okay, well, the value pointed to from index from the right is greater than the pivot. Is that true? No. So we're going to stop there as well. We didn't move our indices at all. We just failed both while tests. And we check our assertion again. Is this value greater than or equal to the pivot? Yes. Is this value less than or equal to the pivot? Yes. Now we get to our if check. Is this index less than this index? It is. So we again are going to swap these values. Again, moving something smaller than the pivot to the left, something bigger than the pivot to the right. And we loop back around, okay? So, and then we increment index from the left up 1, decrement index from the right down 1. And we loop back around. Well, the array at position index from the left is less than the pivot, is it? Yes, this is true. So we increment index from the left. And we do that while check again. Is this value less than the pivot? No, so we stop. We go to our next while loop. Index from the right. So is this value greater than the pivot? No. 4 is not greater than 4, so we stop. And then let's check our assertion. Is this value greater than or equal to the pivot? Yes. Is this value less than or equal to the pivot? Yes. Is this index less than this index? It is, so we swap these values. And then we increment index from the left and decrement index from the right. Now we go back up to our while loop. While is the element at this position less than the pivot? It is. So we increment index from the left. Is the value at, and now we check it again. Is the value at this position in the array less than the pivot? It is. So we increment index from the left. Is the value at this position in the array less than the pivot? No, so we stop. Move on to our next while loop. Is the value at this position in the array greater than the pivot? No, so we break out of that while loop. And now we again look at our assertion. Is the array at index from the left greater than or equal to the pivot? Yes. Is the array at position index from the right less than or equal to the pivot? Yes. But now we get to this if check. Is index from the left less than index from the right? It's not. So now our indices have crossed over each other, and that's when we break out of this loop because we set done to true. So now we are done with the main while loop of the partition method. But there's one last thing we have to do. We have to swap the values stored at the pivot index and the index from the left. So this is index from the left, and this is our pivot index, and we swap these. So in our case, we're swapping the 4 and the 6. And then we are saying that our pivot index gets the index from the left. So pivot index now points here. And that's what's going to be returned is the pivot index, which is going to be 7. Now what you can see here is that everything to the left of position 7 is less than or equal to the pivot, and everything to the right of position 7 is greater than the pivot. So the pivot is now in its final place. This 4 is in its final sorted place in the array. Everything to the left of it is less than or equal, and everything to the right of it is greater than. So this is what will be returned to the quicksort method, and the quicksort method will now recursively call the partition method on this portion of the array, finding a pivot and doing the partitioning, and also on this part of the array, finding a pivot and doing the partitioning. So that's what the partition method does. It looks moving in from the left, stopping when it finds something bigger than the pivot, moving in from the right and stopping when it finds something smaller than the pivot, and then swapping those things. And then continuing in, looking from the left, looking from the right, when it finds values, swapping them. And then when those two left and right indices cross over, we're done with the partition. We put the pivot in the right place, and then we're completely done with this method. So quicksort can tend to be a little confusing, but I think tracing it out actually really helps, so I encourage you to do that. Well, actually, I'm requiring you to do that for the homework, but I encourage you to do it first for practice because I think it helps get the idea of how these indices work. There's so many variables going on with the index and the pivot index, but if you just kind of trace it out, you can really see how this starts to shape up. And the main thing to understand here is at the end of this partition method, we've got one element in its proper place, and everything to the left of it less than or equal to, and everything to the right of it greater than.